So we will now study what happens when we want to use blocks with factorial designs. So let's say that we want to make a full factorial design with 3 factors. So we will need 8 runs to perform the experiment, but we cannot execute more than 4 experiments per day, and we expect that there are differences depending on the day, so we need to do blocks. So for instance, here we have the full factorial design, so we have the all 8 runs that we will do, and the problem is that we may assign okay, so let's say that on day 1 I will do these experiments in blue, and then on day 2 the ones in red. Let us count the number of unknowns that we have. So we know that from the full factorial design we have the intercept and the main effects, the second order effects, and the third order effect. So we have 1, 2, 3, 4, 5, 6, 7, and 8 unknowns. But we have added the block, and we have only 8 runs, and we have to estimate 9 parameters. So we see that we have a problem. Not all of them will be can be estimable. Okay, so can be estimated. Okay, so let's rearrange the treatments by colors. So we put all of them in day 1 together, all of them in day 2 together. And what we see is that, for instance, this ABC has the same sign here and the opposite sign there. So we have confounded the ABC. So ABC has been confounded with the day. And the same happens for AB. AB has also been confounded with the day and also A. So some of the effects of the main effects and the second order effects and the third order effects have been confounded with the day. So it happens as what it has happened, like what happened with the fractional factorial designs, that we have been able to analyze the confounding pattern, but are we able to design it? And the answer is yes. So the only way of escaping from confounding is by replication. So with only one execution of this full factorial design, we are not able to estimate 9 parameters. We need more measurements. We will have to replicate the experiment again so that we are able to estimate the effects of the blocks. Okay, so this is an even more extreme case. So let's say that instead of 4 experiments per day, you can do only 2 experiments per day, and then you decide to sacrifice the BC interactions. Okay, so the BC interactions we have here BC. BC is confounded between day 1 and day 2, and it is also confounded between day 3 and day 4. And in general, we will use some confounding equations, and for these confounding equations it is useful to revise again this algebra in which we had confounding patterns. So for instance, let's say that we have the fact of the combination ABC with BCD. So you multiply the two, remind that all these variables are columns of +1 -1. So when you get a B squared, for instance here, you get A, B squared, C squared, D. So B squared, C squared disappear because they are 1. So this product is AD, this product is this one, and this one, A squared disappears, C squared disappear, and the B squared that is inside the B cube disappears also, so we have only B. So in our example, we have decided to confound BC and ABC. yeah, we were talking BC, but also ABC is also confounded. So ABC is confounded between day 1 and day 3, and day 2 and day 4. Okay, so we have also confounded. So we have decided to confound BC and ABC with the blocks, but then that means that A is also confounded, because in this generalized interaction algebra, A is also confounded. Let us look at A. Again, A is confounded. Yeah, so A in day 1 is confounded with A in day. So day 1 and day 3 they're confounded, and day 2 and day 4 they are also confounded. So let's say that we have so how to design these experiments. So let's say that we have 5 factors, each one with 2 levels, and then with the full factorial will need 32 different treatments, but we have to allocate them in 8 blocks of size 4. So we will perform these 32 treatments in 8 blocks. So we need to confound 7 of these treatments, and 7 is 2 to the 3 minus 1, and 2 to the 3 because we have here the 8 blocks. Okay, so let us choose 3 treatments to confound. So we have decided to confound these second order interactions and this third order interaction, and now we can construct the other 4. So we will confound 7 of them. We have chosen 3. The remaining will be constructed by this generalized interaction. So we multiply AD times B, and then AD times CBC, and so on. So these are the other effects that we are confounding. So we are confounding fourth order effects, third order effects, and so on. Okay, so now we write the treatments in a standard order. So we start with the intercept, and then A, B, AB, C, AC, BC, ABC, and so on. And this has a length 8 because we have 8 blocks. And then we construct the principal block. So the principal block, a treatment belongs to the principal block if it has an even number of letters in common with the generating confounding treatments. So our generating confounding treatments were these ones. Okay, so if a treatment in any one of these has an even number of letters in common, then it belongs to the block 1. Okay, so 1 doesn't share any letter with this, so that means that it shares 0 letters, but 0 is an even number, so it belongs to the principal block. So then we have ACD. ACD shares 2 letters with this and also 2 letters with this, so it belongs to the standard block. And BC, it's the same, so it shares 2 letters with this one and 2 letters with this, so it is it belongs to the block. There is another treatment, another rule, that is, if 2 treatments belong to the principal block, so the generalized interaction also does. So we have this ACD times BCE, we multiply, and we have ABDE. So just a reminder, so what does it mean? This will have low in all factors, this will be high in factors A, C, and D, this will be high in B, C, and E, and so on. Okay, so now we have constructed the principal block. This is the principal block, and now we construct the rest of the blocks by multiplying the first block by the head of the columns. So the head of the columns are these ones. So we multiply the block by 1. So what we have is block 1 again. Now we multiply this block by A. So if we multiply 1 by A, we have A. ACD times A have CDE because the A squared disappears. And then we have BCE times A and ABDE times A. And now the first block multiplied by B, this one. The first block multiplied by AB, this one, and so on. Now we have all the blocks and the 4 runs that we have to run in each one of the blocks, but we have designed it. So it is not that we are able to analyze what are the confusion patterns, but now we are able to design it. And here is a more advanced example. So let's say that we want to test the effect on maize growth on 2 levels of nitrogen, 3 spatial arrangements, 2 management systems, and 2 maize genotypes. So the previous example, we were restricted to factors with only 2 levels. Now we can have any number of levels. So that is why it is called mixed level factorial designs. So it is a factorial design in which each one of the factors has whatever number of levels. Let's say that for doing this experiment, so these are 24 possible combinations, and for doing this experiment we have 4 blocks of 12 plots each. So we want to estimate all main effects and interactions, these interactions. So we have second order interactions and 1/3 order interaction. So let's see if we can make a design to estimate all these. Okay, so let's start counting a number of degrees of freedom. So the genotypes were kind of optional. So let's start making the analysis without the genotypes. So if we don't estimate for the genotypes, we have 4 blocks, so we need 3 degrees of freedom for the blocks. We have 2 levels of nitrogen, so we need 1 degree of freedom for the nitrogen, and yeah, you count the number of degrees of freedom. We had 4 blocks of 12 plots, so that means that we have in total 47 degrees of freedom. That is 48 minus 1. If you count how many degrees of freedom you are spending in estimating parameters, you are left with 33 degrees of freedom for the residuals. So this is a lot. The genotypes is only 1 degree of freedom, so we can include it in the analysis. Okay, so we include it, and in general we say that we will be able to estimate the main effects of a factor, so let's say G, if each level of this factor appears the same number of times in each block, and it appears with each of the combinations of the rest of the factors. And okay, so let's see G. So let's do the analysis for G. So let's say that we have these 2 replicates. So in these 2 replicates we have all combinations, so we will analyze whether G appears the same number of times in each one of the blocks. So here we have 2 blocks, so we count how many times G1 appears here, so it appears half of the times, and also in the second block it also appears half of the times. So it is fulfilling this condition that each level must appear the same number of times in each one of the blocks. Okay, so the other condition is that it must appear with each combination of the rest of factors. So let's look at the factors NSM, for instance. So NSM was one of the factors that we wanted to estimate. Okay, so let's look at NSM. So we have N1, S1, M1, N1, S2, M2, N1, S3, M1. So we have all the combinations here. And for each one of the combinations, we see that, for instance, N1, S1, M1, we have G1 and G2. N1, S2, M2, we have G2 and G1, and the same for all of them. So the factors G1 and G2, or the levels G1 and G2, appear with all the other combinations of the rest of factors. So if that happens, then we will be able to estimate the main effect of G. And we can repeat this analysis for N, S, and M. And yeah, so it is a little cumbersome to make these checkings, but they can be done. To be able to estimate the second order interactions, each combination, for instance, one of them is Gn. So each combination must appear the same number of times in each one of the blocks. So here we are highlighting a few of them. So we have N1G1, it appears in the first block, and it appears also in the second block. And so for instance, N1G1 appears 3 times in the first block and 3 times in the second block. N1G2 appears 3 times in the first block and 3 times in the second block. And the same happens with the other combination, but we are not highlighting them. And then they must appear with each combination of the Sm factors. Okay, so we have N1G1, it appears with S1M1, S3M1, S2M1, and then S2M2, S1M2, S3M2. So for each combination of S and M, we have N1G1, and the same happens with N1G2 and all other combinations. So if this happens, then we will be able to estimate the second order interactions, this Gn. And third order interaction, the condition is all the time the same. So each combination must appear the same number of times in each one of the blocks. So for instance, here we have N1, S1, M1 appears only once in each one of the blocks. And so NSM we will be able to estimate, and it must appear with each combination of the rest of factors. So N1 S1 M1 appears with G1, and it also appears with G2. But this doesn't happen for S3 M1 G1. So you see that S3 M1 G1 only appears in one of the blocks. So that means that we will be able to estimate NSM, but we will not be able to estimate SMG. So the third order interactions between S and M and G. So yeah, so now we have again our 48 or 47 degrees of freedom. Now we analyze which are the interactions that we will be able to estimate. So we will be able to estimate all these second order interactions, and these so we have said that SMG will be confounded. So yeah, this will not be able to estimate, but we can estimate them, but we know that they are confounded. And still the number of degrees of freedom that we are spending here is very low. So we still have 24 degrees of freedom for all the other for the residuals. So we will have presumably quite a high power in each one of the main effects and second order interactions. And the third order interactions at NSM will be able to be estimated without any confusion, but the other two, they will be confounded with the blocks. So the classical designs have concentrated in completely confounded blocks or factors. So for instance, SMG is completely confounded here, or completely unconfounded effect. So NSM was completely unconfounded. But now with computers we may have partially confounded parameters. And I think the point to see this is that when we have some measurements, let's say that we have some measurements y. So this y, in a regression setting, part of it will be given by the factors. So this is the regression part that we were putting in here. So where was it? Here. So this part is coming from the factors, while some other part is coming from the blocks. So we will have a couple of matrices. So we will have a matrix for the factors and a matrix for the blocks. And this theta and this beta will be the effects of the factors and the effects of the blocks respectively. So now we can expand our designs so that we maximize something. So we maximize, for instance, the covariance matrix of the least squares estimator. So we want to maximize the determinant of this thing. So it is to find the x and z. So those are the design matrices, or the combination of blocks and factors, such that this thing is maximized. The determinant of this matrix is maximized. And so this is the same that this design expert was doing. We saw it only with the matrix x, but now if we have x for the factors and z for the blocks, then we can find these optimal designs that are taking care of the covariance of the estimators. Okay, so this would be all for this block, and see you in the next one, that will be response surface.